real zeros of polynomial functions. Because of course there might also be imaginary zeros of our polynomials. Sometimes we get imaginary solutions if we have like a negative under a square root. We just want to look at some ways that we can find the real zeros, however, of those functions. So to begin with, they talk to us on page 160 about polynomial long division. Now, long division was probably your favorite thing in the whole wide world when you were in lower school, right? So, good idea for us to review back through the rules of regular long division, and then we can look at polynomial long division. So, when you did long division as a kid, all right, if you were dividing, let's see, the example that we have up here is 6,599 divided by 21, right? The steps that we usually went through were step number 1, we would estimate. So we would approximate, if we didn't know how many times 21 went into 65, which when you're 8 you don't, we would estimate by looking at how many times 2 would go into 6. And so we could say 2 goes into 6 3 times. So step number 2, we would multiply. We would take the 3 and multiply it not just by that 2 that we had estimated with, but with that whole 21. I know that sounds silly right now, but that'll be important in just a minute. So we'll take 3 times 2 is 6, and 3 times 1 is 3, and then we would subtract. So that was our third step, was to subtract. 65 minus 63 gave us 2, and then we would bring down the next number, and then we would start all over again. So again, we would say how many times does 2 go into 2? 1 time, and then we would multiply that 1 by both of these numbers over here, not just the one we estimated with, and then we would subtract, and then we would bring down. And we kept going with that process until there was nothing left to bring down. When I subtracted and there was nothing else to bring down, then anything that I had left down there was my remainder. All right, so let's apply that same process to a polynomial. I'm going to start with estimating. I don't know how many times x minus 2 is going to go into 6x cubed minus 19x squared. So I'm going to estimate with the first piece. I'm going to say how many times does x go into 6x cubed. Now, whichever way you thought of this over here is what is going to be most natural for you over here. This is what I'm talking about. Over here, when you say how many times does 2 go into 6, in your head, you personally either say 2 times what is equal to 6 to get 3, or you, in your personal brain, say 6 divided by 2 is equal to 3. Whichever way you do that over here is what's going to feel most natural for you over here. So some of you are going to say x times what gives me 6x cubed. Oh, that would be x times 6x squared. Others of you are going to say 6x cubed divided by x gives me what? Oh, that would be 6x squared. So again, over here, if you say 2 times what is 6 to get 3, then over here you're going to say x times what is 6x cubed. But if over here you say 6 divided by 2 is what to get that 3, then over here you're going to want to say 6x cubed divided by x gives me what? 6x squared. Okay? So in either case, once we get our 6x squared, the next step is to multiply. And we kind of jokingly said over here, when you got that 3 and you multiplied, you didn't just multiply it by the number you estimated with, the 2. You multiplied by that whole divisor, that whole 21. The reason we stress that is the same thing is going to be true over here. I'm going to do 6x squared, not just times that x. I'm going to do 6x squared times x to get 6x cubed, and I'm going to do 6x squared times negative 2 to get negative 12x squared. If I have done this correctly, these first terms will always be the same in polynomial long division. They won't always be the same in regular long division, but in polynomial long division they will. Okay? So then our next step was to subtract. And over here when we subtracted, again, we didn't just subtract the 6, we subtracted that whole 63, right? Same story over here. I'm not going to subtract just the 6x cubed. I'm going to subtract that entire thing. That's important because if I subtract that entire thing, it's going to change every single sign, right? So I usually put that in parentheses so I don't forget that I'm subtracting that whole quantity. So I change every one of those signs. So that would be minus 6x cubed, and minus a negative would give me plus 12x squared. All right? So again, if I've done this correctly, this first term is going to cancel out every time, just leaving me 0. But then over here, a negative 19 and a positive 12 is going to give me a negative 7x squared. And then we'll bring down and start the process all over again. So I'll bring down my next term. My next term was 16x, so we'll bring that down and we'll start over. So first step is estimate. How many times does x go into negative 7x squared? Negative 7x, yes. So I can say x times what is negative 7x squared to get the negative 7x? Or I can say negative 7x squared divided by x gives me what to get that negative 7x? All right, then I'm going to multiply. So we'll multiply the negative 7x times x, and we'll multiply the negative 7x times negative 2. Then we'll subtract. And again, when we subtract, we're going to subtract every one of those terms. It's going to change every one of those signs. So we had a negative 7x squared, it'll become positive. We had a positive 14x, it'll become negative. If I've done this correctly, these should cancel, and they do. And now I've got 16 and negative 14, which would give me a positive 2. Next step is to bring down. So we'll bring down our negative 4, and we'll start over again. So how many times does x go into 2x? 2, So if we say 2 times x, that's 2x, and 2 times negative 2 is negative 4. Then we'll subtract, and again that's going to change both of our signs, so this changes to a negative and this changes to a positive. 2x and negative 2x go to 0 as they should, and in this case negative 4 and positive 4 also go to 0. There's nothing left to bring down, so I know that I'm done. That's my remainder. So I have a remainder of 0. So that's our polynomial long division. Now that we understand kind of how that works, let's look at how it can help us and what we could use it for. If they asked me to divide 6x cubed minus 19x squared plus 16x minus 4 by x minus 2, it's kind of like if you're told to divide 30 by 5, okay? When you divide 30 by 5, you get 6, right? And that means that 30 and 5, that 5 and 6 are both the factors of 30. So if we take 30 and we divide it by 5, the other factor that we get is 6, and that means that if I take 5 times 6, I'll go back to that 30. The same thing is true here. We just took that cubic and we divided it by x minus 2. The answer that we got, that 6x squared minus 7x plus 2, that's my other factor. One more time. If you took 30 and you divided it by 5, the answer you would get is 6. That's the other factor. 5 times what is 30? 5 times 6, right? So if you take this cubic and you divide it by x minus 2, the answer that you get is your other factor. So we just found a way to factor that cubic where I didn't have a way to factor it before. It had 4 terms, but it didn't have a common factor, and it wouldn't factor by grouping. So I had no other way of factoring it. The polynomial long division gives me a way to do that. So if I know one of the factors, then I can find the other one. You might also remember that when you did long division as a kid, you were always supposed to check it, right? And the way that you could check that was you would take your answer multiply it by the divisor, and add the remainder, and you were supposed to go back to what you had been dividing into, right? So if you took your answer, your quotient, and you multiplied it by your divisor, and you added your remainder, then you got your dividend, the thing that you were dividing into. So we would check it by saying, okay, my divisor times my answer plus my remainder is supposed to give me my dividend, and sure enough it did. I can check these the same way. I can go back and say, okay, if I take what I was dividing by, my divisor, and I multiply it by the answer that I got, my quotient, that should take me back to what I was dividing into, my dividend. And sure enough, if I take that x minus 2 and I multiply it by that quadratic, I do go right back to that cubic. So that gives me a way to check it, because of course our remainder was 0 here, so there was nothing else to add in. So that is our polynomial long division. But that's kind of a lengthy process. Like, it'd be really nice if there was a faster, easier way to do that. And in some cases there is. Not in all cases, but in some cases there is. In the case when I am dividing by something that is in the form of x minus k, I can use something called synthetic division. Synthetic is exactly what it sounds like. It's like an imitation, or a kind of like a fake version of it, but it still yields our result. So if we are going to have something in the form of x minus k, here's how we can use synthetic division. We're going to come out here in a box, and we're going to put the k value. Now, if you'll notice, since this is x minus k, it's kind of like the opposite of that number right there. So I'm going to put, in this case, that 2 in my box. And then I'm going to copy the coefficients of my polynomial. So 6, negative 19, positive 16, negative 4. I'm going to copy those coefficients across the top up here. In synthetic division, I'm going to take that first coefficient and I'm going to bring it straight down. Then I'm going to multiply that number times what's in my little box over here. So I'm going to take 6 times 2 and get 12, and I'm going to bring that over to my next column. And then I'm going to combine that column. So negative 19 and 12 is negative 7. Do that exact same thing again. Take the negative 7 and multiply it times the 2, that'll be negative 14, and bring it over to the next column. So we did negative 7 times 2, got negative 14, and brought that over to that next column. So now if we combine that column, 16 and negative 14 is going to give us positive 2. Do that same thing again. Take that 2, multiply it by what's in the little box, that 2, and put it over in your next column. That would give us 4 in that next column. And then combine that column. That's synthetic division. And look what it just gave us. Up here, our answer had been 6x squared minus 7x plus 2. 6, negative 7, positive 2. It is giving me the coefficients of my answer. So all I'll have to do is say, okay, when I started, I had x to the third, and I was dividing it by x. So my first term is going to have to be x squared. I had x cubed, and I was dividing it by x, so that first term is going to have to be x squared. Then once I get that first term, then it's just going to go in descending power order. So this is x to the second, this will be x to the first, this will have no x, it'll just be my constant term, and then that last number will be my remainder. And you'll notice that's the exact same answer that we got just a second ago. Okay? So polynomial long division and synthetic division. Again, the reason that we have to learn the polynomial long division is because this synthetic division only works when I'm dividing by something in the form of x minus 2 or x plus 5 or something like that. It's got to be in that form of x minus k, or I can't use the synthetic division. I have to use the polynomial long division. All right, let's look at another one. We've got x cubed minus 5, and we want to divide that by x minus 1. All right, so let's do it by long division, and then we'll see if it qualifies to do it by synthetic division. All right, so if we do this by long division, we start off with estimate. All right, so how many times does x go into x cubed? X squared times, right. So we can go through then and multiply. X squared times x is x cubed, and x squared times negative 1 is negative x squared. And then I get ready to subtract, and I have a problem. I can do x cubed minus x cubed, but I can't do like negative 5 minus a negative x squared. Like, those aren't like terms. It's not lining up. Like in the last problem, everything was like all nice and neat and it all lined up just perfectly. How come this one's not lining up? The reason this one isn't lining up is because it skipped some terms. See how it goes from x to the third to the constant term? Like, there's no x squared term or x to the first term. So it's like I've lost my place values. It'd be kind of like I was trying to have 1005 and divide it by something. If I don't have something in the hundredths place or something in the tens place, I have to put zeros in there to hold the place, right? Exact same thing with these polynomials. If I have any missing terms, I need to put in 0 placeholders in order to get this thing to line up the way that it's supposed to. So anytime they skip a term, like we went from x to the third to the constant term, so they had left out the x squared term and the x to the first term, I want to put zeros in for those. I need placeholders, okay? Now when I go to do the division, it'll work just fine. So if we go through now, we can start that same way. You had already told me that x cubed divided by x was going to give me x squared. So now when we multiply, x squared times x is x cubed, and x squared times negative 1 is negative x squared. Now it's lining up. So we'll subtract. That changes both of our signs. And then we'll combine. So x cubed minus x cubed should drop out, and it does. 0x squared plus 1x squared gives us x squared. And then we'll bring down our next term. So how many times does x go into x squared? X, And then we'll multiply. So x times x and x times negative 1. We'll subtract, changing both of our signs. And then we'll combine. First term drops out as it should. No x and 1x gives me 1x. And then we can bring down our next term. How many times does x go into x? 1. Multiply, subtract, changing both of our signs, combine. And when I get to the point that there's nothing else to bring down, like there's nothing else here that I can bring down, then what I'm left with is my remainder. All right, now could I have done this problem by synthetic division? Does it qualify? Yes. So if I were going to do this by synthetic division, this is in that x minus k form. What's going to go in the little box right here? Positive 1, right. It's like the opposite of that number right there. Oh, one other thing I want to mention to you. You know how we said that you have to put in 0 placeholders if you skip any terms in your dividend? You have to do the same thing in your divisor. If you were dividing by x squared minus 1, you're going to have the same problem if you don't go in and put in a placeholder for any term skipped. So whether it's in your divisor or whether it's in your dividend, if they skip any terms, you need to fill in a 0 placeholder so that you can get those things to line up. By the way, if this had been being divided by x squared minus 1, could you use synthetic division for that? No, not in that x minus k form. Okay, so in that case, I would have to do the long division. Okay, So you told me that for my synthetic division that I was going to put a 1 in my box. And notice that even in synthetic division, when I put the coefficients across the top, I still need those placeholders or I'm not going to get the right answer. So whether you do the regular division or the synthetic division, either one, you need those placeholders. All right, so with synthetic division, how do we start? Bring down the 1. Then what? All right, multiply the 1 by the 1 and put it in the next column. Add those, yep, so that'll give me 1. And then what? All right, multiply the 1 by 1 and put it in the next column. Combine those, multiply the 1 by 1 and put it in the next column. Combine those. How do I know what to start with over here? This is 1 what? X squared, right. Because I had x to the third being divided by x, I know my first term then is going to be x squared. And then it's just going to go descending power order from there. 1x squared, 1x to the 1, 1x to the 0 is in essence what it is, because x to the 0 is 1. But basically just our constant term. And then that last number will be our remainder. And we're not going to write r negative 4 for our remainder. A little more mature way of writing that remainder is to take that remainder and write it over our divisor. So since we were dividing this by x minus 1, then we would just say negative 4 over x minus 1. Because that's the part of the whole that I have remaining. All right, so once I know how to divide my polynomials, either by polynomial long division or by synthetic division, then there are a couple of really cool shortcuts that I can apply. They give me on page 164 the remainder theorem, okay? And they tell me that if there's ever a time that you just want to know the remainder, you do not have to do the long division to get it. You don't even have to do the synthetic division to get it. If I just wanted to know when I take x cubed minus 5 and I divide it by x minus 1, what remainder do I get? There's a fast, easy way to find that. If I'll take the k value, okay, now remember this is x minus k, so that k value is what we put in the little box right there, same thing, okay? If I'll take that k value, in this case 1, and I will plug it into the function, the answer that I get will be the remainder. So I could go through in this function, it was f of x is equal to x cubed minus 5, and k was equal to 1. So if I put 1 in the place of x, I'll get 1 cubed minus 5, I'll get negative 4, I'll get my remainder. Okay, why would I ever want to just know my remainder? That's kind of pointless, right? Not when I get to the factor theorem, because the factor theorem says if your remainder is 0, so that's where I would want to know what my remainder is, okay? The factor theorem says if your remainder is equal to 0, then what you were dividing by is a factor. But if your remainder is not 0, then what you were dividing by is not a factor, right? Go back to the scenario we had earlier today. We talked about if you took 30 and divided it by 5 and you got 6, that meant 5 and 6 were both what of 30? Factors, right? So we go through and we say 30 is divisible by 6 because 30, when you divide 6 into 30, it divides evenly, right? I don't know how you divide oddly, but we've always said divide evenly. What do we mean by that? No remainder, right? Or we get a remainder of 0. So if you can divide 30 by 6 and get 5 with a remainder of 0, that meant that 5 and 6 were both factors of 30. But if I took 31 and divided it by 5, I would get 6 with a remainder of 1. Are 5 and 6 factors of 30? No, because it doesn't divide evenly, right? Basically, it just means because we get a remainder other than 0. That is exactly what my factor theorem is saying. My factor theorem is saying if you take a polynomial and you divide it by x minus k and you get a remainder of 0, that means that x minus k was a factor of that polynomial. But if you get any remainder other than 0, then that means that it wasn't a factor. So that's where the remainder theorem will be really helpful. Because if they asked me back here, is x minus 1 a factor of x cubed minus 5? I don't have to do this. I don't even have to do this. All I would have to do is just plug 1 into that function and find out that I got a remainder of -4. So is it a factor? No, because the remainder wasn't 0. But if I had plugged in 1 and gotten a remainder of 0, then I would say, yes, it is a factor. So literally, that would be all the work that I would need to do to be able to tell whether the one was a factor of the other, instead of having to actually do the division.